afternoon, everybody. I hope you're doing fine. Hello, Defiant Tuber. Hi, Ritik. Welcome to the session. Okay, so I welcome all of you to the JEE Byte session for thermodynamics. Okay, so this is our first session based on this chapter, and we will be having two sessions in total for dynamics particularly. Okay, and in the first session we will be dealing with the first law of thermodynamics, and along with this we will deal with thermochemistry. In thermochemistry particularly, we will be looking at questions based on the Hess law. Okay, in the second session we will be discussing questions based on the first and second law of thermodynamics along with the Gibbs-Helmholtz equation. All right, so that's a very, very important equation when it comes to JEE exams. Hello, Aradhya. Good evening. Okay, so let's get started. Hello, Hare Krishna. Okay, so mind you guys, thermodynamics, as we all know, it's a very, very important chapter from the JEE point of view. Why? Because there are 2 to 3 questions asked from this chapter in one JEE exam. Okay, so that is like really important for us. It will fetch us 8 to 12 marks, right? Hello, everybody. Hello, Smriti. Hi, Exile Gaming. Hello, everyone. Okay, so let's get started with the session. Let's deal with the first question. And it was asked in JEE Mains 2017. Okay, so very recent one. So here the question says delta U is equal to which of the following? Now, when I look at the options, what do we see? These are different kinds of works which are given to us, right? The work done. Okay? Okay, Dev. All right. Welcome, everybody. Now, let's focus on the question, please. Okay. Okay, so Kundan says isothermal work. Okay, let us see if your answer is correct. All right. So let's look at each of these options individually and try to understand what information can be gathered from here. This is isochoric work. Iso, all of you remember, it means same. Okay, similar, at same or constant condition. Isochoric refers to constant volume. Isochoric refers to constant volume. All right, and when the constant volume is constant, the initial and final volume are the same, so delta V is equal to 0. In this case, when work done is equal to minus P delta V is 0, so work done is 0. Okay, and in no case will delta U become equal to 0 when I have isochoric conditions, right? So the first law of thermodynamics, what does it say? Delta U is equal to Q plus W. Right? So if W is 0, then delta U becomes equal to Q, right? Okay, Meghna. Next option is isobaric work. This means the condition of constant pressure is given to us. Okay? Condition of constant pressure is given to us. Now at this particular condition, delta U will not be equal to isobaric work. We will have some value of Q as well here. Right? Let's look at the third option, adiabatic work. What does adiabatic condition represent? Adiabatic condition represent that there will be no heat transfer from the system. Okay, from or to the system. That means I can say under adiabatic conditions Q is 0 here. So delta U becomes equal to W. Which work done? Work done under adiabatic conditions. Okay. So till now option C is seeming to be correct. Right. Next we come to isothermal work done. Isothermal represents constant temperature conditions. Constant temperature, that is delta T is equal to 0. Now under conditions of constant temperature, we know there are different formulae for work done under reversible, irreversible kind of systems, right? Now this is really important for you to understand. Work done here is not equal to 0 until and unless some special conditions are provided to us. So W isothermal is not necessarily equal to 0. However, we have a special formula for delta U, that is NCV delta T. So when delta T is 0, that is I have isothermal conditions, delta U becomes equal to 0, right? If RHS is equal to 0, LHS also becomes equal to 0. Now, is isothermal work equal to 0 necessarily? No, it is not. Therefore, option D is not the correct answer. So this is option C, where we have adiabatic work, Q will be equal to 0. So delta U becomes equal to W adiabatic, right, Aradhya? So C is the correct answer. Excellent, Meenakshi. Very nice. Okay. So this was a fairly easy question for us, right? It was directly based on the first of thermodynamics. It was it involved a little bit of your understanding about different processes: isochoric, isobaric, isothermal, and adiabatic. That's it. Okay, let's move to the next question. Okay, now here we will talk about the Hess law of constant heat summation. Hess law of constant heat summation. So questions based on this Hess law are very, very easy, and they have been asked in almost every year. Okay. What does this Hess law tell us? Yes, Sandeep. Okay. So this Hess law tells us that if a particular reaction is occurring in multiple stages or in multiple steps, okay, then how do we calculate the enthalpy of reaction? It is calculated as the sum of all the enthalpy changes taking place in the individual reactions. All right, we just need to add them up. Obviously, we will look at whether for the individual reaction a negative sign is coming in or positive sign. But if let's say a reaction is occurring in 3 steps, okay, and the first step has enthalpy H1, next has enthalpy H2, next has enthalpy H3. So total enthalpy of reaction will be equal to H1 plus H2 plus H3. Okay? All right. Now once again. So let's look at this question. It says the heat of combustion of carbon. Now there are two terms that we will understand here. The heat of combustion of carbon and carbon monoxide are given to us. The heat of formation in kilojoules of carbon monoxide per mole is which of the following? Maybe C, maybe. Okay, Ahir, you need to be confident. All right. Which kind of enthalpy? Here we are talking about the enthalpy of combustion, Jitanshu. Okay. Now we need to understand what do we mean by heat of combustion or heat of formation. So let's pay attention here. So the first statement is heat of combustion of carbon. Okay. Combustion means burning of a substance in the presence of oxygen. Okay. So when I take carbon in solid form and I burn it with enough oxygen, this will give us CO2 gas, right? As we see, the equation is balanced here, right? The equation is balanced, so we do not need to do anything. Just let us assume this is reaction number 1. Okay. And delta H for this reaction is minus 393.5 kilojoules per mole. Excellent. For the second one, we will see an abnormality there. And we need to understand that concept. This is now carbon monoxide reacting with O2. This will also give me CO2. But is the equation balanced? Is the reaction balanced here? No, it is not, right? So there are two ways of balancing this reaction. One is I can write 2CO plus O2 gives me 2CO2, right? The equation becomes balanced. Or we can write this as CO plus half O2, very good, gives me CO2. Right? Now, which of the two reactions should we need to consider or do we need to consider to answer the question? Now, pay attention. This is heat of combustion. So remember, there are different kinds of enthalpies depending upon the reaction which is taking place. Okay? So heat of combustion we would need to fix 1 mole quantity for the substance that is getting combusted. Okay? For heat of combustion, we need to put 1 mole of the substance getting combusted. So taking this equation that I've written with 2CO, this is incorrect. Okay? It will not have enthalpy equal to this. Which equation we will take? Where the coefficient of CO is 1. All right? So CO is the substance getting combusted. We will put 1 mole here and then try to balance out the rest of the equation. This is for heat of combustion. Okay. Now this is the second equation. We need to calculate the resultant equation. Let's see what is our resultant equation. It says the heat of formation of carbon monoxide. So we need to form carbon monoxide. Now again remember. Okay, Jitanshu, just pay attention here also we are applying the same concept. Again remember, this is now heat of formation, right? Heat of formation may, this means what is the energy change occurring in the reaction when 1 mole of that particular substance is formed. Okay, when 1 mole of that particular substance is formed. So I need to fix 1 mole of this carbon monoxide getting formed. Okay, so how can it be formed? It is taken like by its constituent particles present in their standard state. So carbon is present as graphite in the standard state. Oxygen is present as O2. Okay, oxygen is present at O2. Gibbs energy will be covered in the next session, random lecture. Okay, so we need to put 1/2 here to balance this reaction. I'm going to repeat this concept again. Okay, 1 second. So for heat of combustion, let's revise. For heat of combustion, we need to fix 1 mole of the substance getting combusted because it represents the enthalpy change occurring in the reaction when 1 mole of a substance, 1 mole of a substance reacts with enough oxygen to give the required products. Okay, so which or where do we need to put 1 mole? At the substance getting combusted. In heat of formation, where do we need to put 1 mole? The substance getting formed. Okay, now we have written the equations as per the question given to us. So this has, let's suppose this is delta H1 and this has delta H2. Okay, next is, this is what we want. Let's say it has reaction enthalpy as delta H. All right. Now, what do I need to do to the two reactions? What operations, mathematical operations can we apply so that I get the resultant equation? What can we do? Think about it. I need carbon, 1 second. We need carbon on the left hand side here. In which equation do I have carbon on the left hand side? In the second, in the first equation. So we need to write the first equation as it is. So operations to be performed, take equation 1 as it is, reaction 1 as it is. Let's write it down. It's carbon solid plus O2 gas. Arrow ke baad we will write CO2 gas. Now when I look at the next component, CO here is coming on product side, but in the second reaction, carbon monoxide is written in the left hand side, right? So if I add the two equations, if I add 1 and 2, I will get carbon monoxide on the left hand side, but that's not what I require in the resultant form. I require it on the right hand side. So what we will do, we will minus or we will subtract the second equation. All right, we will subtract this second equation. Let's try to do that. Remember, when we subtract it, it means I am reversing the equation. I can write here minus 2CO, or I can write CO on the right hand side directly. So what we will do here, we will write 2CO. Oh, sorry. We need to look at this one. I'm sorry. This will be 1CO. Okay. And plus half O2. And here we will write CO2. Right? Hello, Akansha. This is clear? Now, after this, let's see what happens. We get from here, what do we get? Carbon plus O2. This is O2 here and this is half O2 here. So this will become 1/2 O2 gives me CO2. CO2 will get cancelled out. CO2 and CO2 get cancelled out. Very easy. Very nice. And we get CO here. Is this representing the resultant equation? Yes, it is. Right. Now, whatever we have performed to the reactions to get a resultant reaction, the same thing will be performed to the enthalpy values. Okay. So delta H becomes delta H1 minus delta H2. Very easy. Delta H1 becomes delta H becomes delta H1 minus delta H2. Is this clear? So just subtract the values and you will get this. What are the values? Minus 393.5 minus of minus. Okay, 1 second. Yeah. Now it is visible, right? Now it is visible? Yes, guys. Is it visible? Can you tell me, is the board visible now? All right. ठीक है. So minus है 283. So you can perform the calculation and it will come out to be minus 110 kilojoules per mole. Right? So that's our correct answer there. Clear? That is our correct answer here. Okay, very nice. Let's move to the next question. That is also based on Hess law only. Okay, this question is also based on Hess law. What do we understand here? Okay. Krishna, it's not positive. Okay, it's not positive 110. It is minus 110.5. Okay, it's not positive. Come on. Look at the board. See, we are subtracting this. This is higher, no? So negative sign will come here. Okay. Please be specific and correct while you perform simple calculations. All right. Now let's move to the next question. Three reactions are given to us and their corresponding enthalpy of reaction in standard state is provided to us. Okay. So we have the reaction C plus O2 gives CO2, H2 plus half O2 gives H2O, CO2 plus H2O gives CH4 and O2. Let's name them as reaction 1, reaction 2 and reaction 3. Okay. The question says, based on the above thermochemical equations, the value of delta R H naught at, no problem Krishna, at 298 Kelvin for the reaction, carbon graphite plus 2H2 gives CH4. So this is my resultant reaction or the required reaction that we want. So we need to perform certain operations, mathematical operations, so that we get the required reaction. So how can we do that? We will just look at it very easily and very fastly. Okay. We want carbon graphite on the left hand side. I have carbon here in the left hand side. So that gives me that I have to write equation 1 just like this. Okay, we don't need to subtract it. We don't need to multiply or divide it by any particular constant. Okay, so this gives me equation 1. Now the next part is it requires a multiple of 2. So it requires 2 here with H2. Okay, in the whole set of equations given to us, where is H2 coming in? Very good, Omkar. Where is H2 coming in? It is coming in the second equation. And in the second equation, it has the coefficient of 1. We want the stoichiometric coefficient to be 2. So what we will do? We will add twice of equation 2. Right? We will add. Why add? Because H2 is on the left hand side on both the cases. In both the cases. Second as well as resultant form. Next one is we require CH4 on the right hand side. Where is CH4 on the right hand side? In the reaction third. Right hand side. So we need to add it up. Okay. We need to add this up. Let us verify if we are getting the resultant what we want or not. Okay, let us verify. So I'm performing the calculation with respect to the elements with reactants here. So carbon graphite plus O2. This is reaction 1, right? Next is we have to add twice of equation 2. So twice of equation 2 gives me 2H2 plus 2 into half, yani ki 1 O2 plus twice of H2O. Please be specific. If you want to multiply an equation by 2, you will multiply the entire equation. Students tend to multiply the left hand side, but they forget to multiply the right hand side. Please be specific. Be sure about your calculations. Okay. All right. Be sure about your calculations. Next is we need to add equation 3 as it is. So we will just add it here. CO2 plus 2H2O plus CH4 on the right hand side plus 2O2 on the right hand side. Okay. So what do we see? Carbon graphite is remaining as it is. This O2 gives me 2O2 gets cancelled here. Right? It gets cancelled here. 2H2 remains as it is. CO2 gets cancelled off with CO2. 2 water gets cancelled out here. Okay. Do we get the required equation? C plus 2H2 giving me CH4? Yes. This is the required equation. Okay. All right. So Abhishek, we need to look at the resultant equation and try to get the equation as a result of mathematical operations performed on the given data. Okay, whatever is there on the left hand side, keep it on the left hand side, add the equation. Whatever is there on the right hand side, keep it on the right hand side. If you do not get, okay, see in the second reaction or in the first reaction per se, if in first reaction, sorry, it is given, this carbon is given to us here, okay, on the right hand side. So हम क्या करेंगे? What we will do? We will subtract this equation. We will not add it, we will subtract this equation. Okay? If it would have been given to us on the right hand side. Okay, so the correct answer here, so we will perform the same on the delta H value. So delta H1 is minus 393.5 plus twice of minus 285, sorry, minus 285.8 plus 890.3. What do we get as the answer? Minus 74.8. All right. What do we get? Minus 74.8. Everybody is getting A? Yes, everybody is getting A. All right. Very nice. Very nice. Let's move to the next question now. These kind of questions have been asked many a times. Okay. Resonance will not be taught right now, Krishna. Okay. Let's look at the question and see what is the new concept that we need to remember here. The combustion of benzene in liquid form, it's given to us, gives CO2 and water. Okay. Remember, water is present in liquid state. Given that the heat of combustion of benzene at constant volume, heat of combustion at constant volume is this much at 25 degrees Celsius. Heat of combustion of benzene at constant pressure we need to calculate. Okay. At constant pressure, we need to calculate it here. How do we do this? So first of all, we should understand what we need to find out, what is given to us. So heat of combustion at constant volume. At constant volume, heat of combustion represents the value of delta U. Okay, it represents the value of delta U here. So that means delta U is provided to us as minus 3263.9 kilojoules per mole. Okay, this is, I'm making you understand, Krishna. Please pay attention now. At constant volume, if some heat of combustion or some heat of reaction at constant volume is given to us, that represents delta U. At constant pressure, that represents delta H. So we need to find out delta H. Delta U is given to us. Okay. Now it's saying which reaction is considered here. The combustion of benzene. All right. So for combustion of benzene, we need to write down the chemical equation. We need to balance it out. So remember, one reaction I'm going to tell you, 1 second. Yes. What is that reaction? General reaction. General reaction for combustion of hydrocarbons. Okay. Hydrocarbons meaning alkane, alkene, alkyne. Everywhere this formula will be applicable, and I suggest you to remember this. So this will be CXHY. Okay, CXHY. Okay, 1 second. Let's use this. This will be CXHY plus O2. Now remember, when any hydrocarbon is burnt, when it is combusted, it gives us CO2 plus water. Okay. Now the stoichiometric coefficients you may remember here. This will be X plus Y by 4. Okay. X moles of CO2 we will get, and Y by 2 moles of water we will get. Okay. This is a very, very important equation for you to remember. Okay. This is important and you guys should remember this equation. All right. Now let's apply this here in the reaction. We have to find combustion of benzene. Right, we have to find combustion of benzene. So that becomes C6H6. So that is X is, one second. X is 6 here and Y is also 6 here. Right. Plus 6 plus Y by 4. So that means 6 plus 6 upon 4 O2 gives me 6 moles of CO2 plus 6 upon 2, that is 3 moles of water. Remember, this water is given to us in liquid form. This is gaseous, this is gas. Okay, and this is liquid given to us. Right? Now let's simplify this. This will become 15 by 2. So I'm just going to write down 15 by 2 here now. Okay, this becomes, when you solve it, it becomes 15 by 2. Now remember, all of you, this is a repetition of a concept we just did. Okay, which one? It is the combustion of benzene. So we need to fix 1 mole here. I cannot change this. All right, we cannot change this. We need to fix this 1 mole here. Okay. Now let's look at this reaction. Delta U is given to us. Delta H we need to find out. Right. Let's find out the delta Ng for the reaction. That is the difference in the number of gaseous moles in product side and difference in number of gaseous moles in the product side minus number of gaseous moles in the reactant side. All right. So how much is it? This becomes 6 moles of CO2. That's only the gaseous component here. And O2 is how much? 15 upon 2. Right. That is 7.5. So we get minus 1.5 equal to delta Ng. Right. So which formula can we apply here so that I get the correct answer? Delta H is equal to delta U plus delta NGRT. Okay, where R is the gas constant, where T is the temperature that's provided to us, we need to take it in Kelvin. Okay, we need to take it in Kelvin. This we need to find, so that means delta U is given to us minus 3263.9. Okay, now guys remember, this is kilojoule per mole. All right, this is kilojoules. Added with minus 1.5, that is my delta Ng, right, into R. Now R की value is 8.314 joules per Kelvin per mole. Right, it is 8.314 joules per Kelvin per mole. Right, and this is given to me in kilojoules. So we need to convert joules to kilojoules. So multiply by 10 to the power minus 3 into temperature. Temperature is 25 degrees Celsius, which becomes 298 Kelvin. So when you find this out, the answer will come out to be minus 3267.6. Okay, such that the correct answer is option D. So what have we understood here? R is given to us in joules per Kelvin per mole. Delta U is given to me in kilojoules. So we need to convert one of the numericals so that they are in the same units. Okay, so that they are in the same units. Otherwise, your answer will come out to be incorrect. Right? All okay. All right. So what did we do in this question? We needed to find delta H. We have delta U, that is at constant volume. We have the heat transfer at constant temperature, at constant pressure. We need to find it out. That is delta H needs to be found out. We want the equation for combustion of benzene. I've given you a general equation. You should remember it. Okay, and just substitute the values. You'll get your answer. Okay. So all the very best for your next session and for your preparation for JEE. I hope to see you in the next session. Bye-bye, everybody. Take care.